Welcome to the hydraulics and hydraulic machines class. So we are discussing unit 4, which is the hydraulic turbines. So in this lecture, we discuss on the velocity triangles and the work done in case of peloton turbine. To be frank, this work done is already done in the impact of jets. If you recollect once where the jet strikes basically at the what center and leaves at the other end, that's what exactly it is. And now that's we will take it up also. Again, there's no issue, but so that part we will take it up. But the velocity triangles first, because in all these cases, velocity triangles work done. So as long as the flow is tangential, naturally the impulse momentum equation is used. The moment flow becomes radial, naturally we use angular momentum principle, even though in both the cases work done is our aim. So here what we will do in the case of tangential flow turbine, we first derive the equation for force using impulse momentum equation and then multiply it by the velocity of vane so that we will get the work done. Whereas in the other case, using the angular momentum principle, we calculate the torque, and from torque we calculate the work done. So that is the only difference. So let us go ahead with that drawing of the velocity triangles and derive the equation for the work done and efficiency and maximum efficiency. So these things we will look into in today's lecture. So again, Pelton turbine continuation, Pelton turbine continuation. Focus is on the velocity triangles and work done. This is the focus. So now let me start draw. The jet of water from the nozzle strikes the bucket at the splitter. That's what we told. The jet of water from the nozzle strikes the splitter, and at the splitter, the jet is divided into two parts, and these two parts of the jet glides over the inner surface of the bucket and comes out at the outer edge. And last, I have shown again. I will draw one more time for your convenience. So this is basically what we thought the how the bucket looks like. So the central portion is this is the splitter actually, and now these are all the buckets, and this there is a cut here. That's how it appears. So now if I take the section of it here, if I take the section of this bucket, then how it appears like that, it appears it will be like this. This is how the bucket looks like. The central portion is the splitter, and this is the edges, both the edges. So now how the velocity triangles will be. The jet strikes at the splitter. This is how the jet strikes, right? This is the absolute velocity, right? And the vane velocity is also in the same direction. So this is vane velocity, right? So they all are in the same direction. So naturally, this will be VR1, because the velocity triangle is a triangle drawn between absolute velocity, velocity of vane, and the other one is the relative velocity. So now in the case of a tangential flow turbine, at the inlet, at the splitter, all are in the same direction. Here the horizontal component of V1 is equal to, that is what we call it as VW1, whereas there is no vertical component, so therefore VF1 is equal to 0. This is how the velocity triangle at the inlet will be. So if I draw the velocity triangle at the inlet, once again, if you see, suppose, so this is how the jet strikes, right? A, B, you can put it. This is V1, right? And AC, you can put this as U1 velocity of the wind, whereas the rest of the thing is VR1. So this is how the velocity triangle is. So now in that, if you see it, V1 is equal to VW1, VF1 is equal to 0, alpha is equal to 0, theta is also equal to 0. And what is VR1 is equal to? VR1 is equal to V1 minus U. This is the first thing. So this is a inlet velocity triangle. Inlet velocity triangle. The jet, after striking the splitter, actually how it leaves, the jet leaves like this. Again, recollect, actually this is tangential. So now if I extend this line, right, this is phi and this is the deflection angle. I'm only drawing on one side. The other side also you can draw. So this is how VR2 will be there, which we know already. And this is U2. And if I join these two, naturally this will be V2. So the outlet velocity triangle is VR2, U2, V2. And the horizontal component of V2 and vertical component are VF2 is the vertical component, horizontal component is VW2. So the outlet velocity triangle, if I take it, the outlet velocity triangle, it comes out with a velocity VR2, then this is horizontal direction is U2, then joining this, it will become V2, right? It's horizontal component and vertical component, both VW2, VF2, and this is phi, and this is beta. So these are the things. So one conclusions are VR2 is equal to VR1 because we assume that there are no losses. Then again, U1 is equal to U2 is equal to U, that is the velocity of the wave. This velocity of the vane is the tangential velocity. So that you should remember. So these are the two things that which we know. Then coming back actually. So after knowing what are the velocity triangles in the case of Pelton turbine, first thing is inlet velocity triangle is a straight line. Inlet velocity triangle is a straight line because the velocity of the vane and the velocity of jet are in the same direction, whereas outlet velocity triangle is beta is less than 90. This is also you should remember. So this is the velocity triangles in the case of that. So now how to move forward. So before moving forward to the work done, what are the things that which we should know it? For example, normally what I told at the beginning is H1 is the head available in the reservoir. That is the gross head. Gross head minus loss in the pipe and loss in the nozzle. Then finally, what is net head available? Net head available. Net head available at the entrance. At the entrance to the turbine. Entrance to turbine is equal to H. This is the net head. So now if I take it, the net head is equal to this. So therefore, the absolute velocity of jet V is equal to root 2GH. Root 2GH. Whereas the velocity of vane U is equal to U1 is equal to U2 is equal to U is equal to pi d n by 60 because the wheel is rotating at an angular speed of n. N is the speed, n is equal to speed of RPM, speed in RPM, right? D is equal to diameter of peloton wheel. So because starting point is how to calculate absolute velocity, how you calculate the velocity of wave. These two should be known. Knowing these two, then knowing the velocity triangles, we let us move forward. Already we have determined the force exerted by the jet in x direction is equal to Fx is equal to rho A V1 into VW1 plus VW2. This already we have derived using impulse momentum equation. Kindly please check it up that. Again, we don't need to derive again here. So there we have derived rho A V1 into VW1 plus or minus VW2. But there beta is less than 90, it is plus is equal to 90, VW2 is 0, greater than BW2 minus. So, but now here beta is less than 90. We can straight away put rho A V1 into VW1 plus VW2. Then what is the work done per second is equal to work done per second is equal to Fx into U. So that is equal to rho A V1 into VW1 plus VW2 into U. So this is the second thing. So work done that which we got already. Then what this work done is, what is this work done actually? This work done per second is nothing but the power supplied to the runner. Power supplied to the runner is equal to work done per second. Right? This is the output. Then what is the input actually? The energy supplied to the jet. The energy supplied to the jet is equal to what? Kinetic energy of jet. Kinetic energy of jet. And this kinetic energy of jet is equal to half into rho A V1 into V1 square. So this is the kinetic. So therefore, hydraulic efficiency is equal to hydraulic efficiency is equal to right. This is equal to power given to the runner divided by kinetic energy of jet. So if I take it, then rho A V1 into VW1 plus VW2 into U divided by half into rho A V1 into V1 square. So this if I cancel, then naturally what will happen? If I take this numerator, theta H is equal to 2 into VW1 plus VW2 into U divided by V1 square. This is the thing. So now let us substitute what is VW1, VW2, that we will see it. So we know basically VW1 is equal to from inlet velocity triangle, right? VW1 is equal to V1. That which fine. Then what is outlet from outlet velocity triangle is equal to what is VW2? VW2 is equal to VR2 cos phi minus U2. Please check the things. If you want, once again, I will draw. So this is VR2, this is phi, this is U2, this is V2, this is VW2, VF2. So if you take it, VR2, VW2 is nothing but VR2 cos phi total minus U2. This is this. Then afterwards, so what is VR2 is equal to? We can write VR2 is equal to VR1 cos phi minus U2. Already we mentioned U1 is equal to U2, right? Then second one, what I mentioned, VR2 is equal to VR1. That's what we have initially. So that is what. Then what I can write, VW2 is equal, VR1 is equal to V1 minus U, right? Into cos phi minus U1. Fine. Now I will substitute all this in that. So therefore, eta hydraulic efficiency is equal to 2 into VW1 is equal to V1 plus this is V1 minus U cos phi minus U1 into U divided by V1 square. So this U also U1 also if I write 2 into V1 minus U, because this U1 you can write it as U plus V1 minus U cos phi into U divided by V1 square, or 2 into V1 minus U into 1 plus cos phi, right, into U divided by V1 square, or eta H is equal to 2 into 1 plus cos phi by V1 square into V1 minus U into U. It is equal to 2 into 1 plus cos phi by V1 square into V1U minus U square. For maximum hydraulic efficiency, U is equal to 0. Therefore, 2 into 1 plus cos phi, this is only constant like which is outside, dou by dou U of V1U minus V1U minus U square is equal to 0. So if I do it 2 into 1 plus cos phi by V1 square into dou by dou U of V1 means V1 minus 2U is equal to 0. Therefore, this as 2 into 1 plus cos phi by V1 square cannot be 0, then V1 minus 2U is equal to 0. Or U is equal to V1 by 2. This is the thing. Therefore, maximum efficiency is equal to 2 into 1 plus cos phi by V1 square into basically the previous one is what? This is V1U minus U square. V1 into U into, if I put it actually, what will be the thing actually I will be getting? It is V1 minus U. V1 minus U means V1 minus U means V1 by 2 into basically U. U is equal to V1 by 2. So if I do it like this, then I will get it 1 plus cos phi by 2. This is the answer I will get for maximum efficiency in the case of Pelton turbine. Right? This then in that case, normally phi in the case of Pelton turbine will be 15 degrees. So kindly you can remember it. But in the case of examinations, if they give other value, if it is 15 degrees, you can calculate what is hydraulic. So this is the velocity triangles plus basically the work done in case of Pelton turbine. So here I will stop this lecture. So we have dealt with the velocity triangles and then work done in the case of the Pelton turbine. So that part we have taken it up. And in the next class, we will go with the working proportions of Pelton turbine. So these two topics are extremely important for problem solving. Velocity triangles, work done, a hydraulic efficiency equation, and then working proportions of a Pelton turbine. So, and design leading to the design of Pelton turbine. These are the important things. So, that in the next lecture, we cover that also. Thank you very much.
Like, share, and subscribe. Hit the bell icon for more updates.